welcome back to the Vishay video series dedicated to electronic simulation with thermistors and RTDs. This is the part 6 already. My name is Alain Stas. I'm a product engineer for nonlinear resistors, and today I would like to review a simulation of a special application for airflow detection. This can be performed with our TFPT 5-ohm SMD RTD. Such component is a SMD thin-filmed linear resistance with the lowest R25 value available from the specification 5 ohm. The built-in model in LTspice for this part is a resistor controlled by two voltages, one acting as a temperature and the other as the dissipation coefficient. The first simulation is done in zero power condition. We sweep the temperature and we compute the resistance of the part with a tolerance on R25 of about 25%. We see that the R25 values are randomly scattered between the minimum and the maximum of the specification. The total RT curve tolerances are in fact fully reproduced throughout the whole temperature range. We can now test virtually the component in dissipation conditions. We apply a bigger current, 100 mA, and we change the airflow rate onto the component by pulsing V1 between 2 mW per Kelvin in still air up to 3.5 mW per Kelvin in the big airflow. The ambient temperature remains constant in this simulation. We see the result of variation of the resistance for a nominal part during this dissipation change. We can now introduce a tolerance on the TFPT R25 and change the ambient temperature at will. We have now a complete picture of how the TFPT will behave in the application. We are now ready to simulate the total application of airflow detection. This circuit is a classical constant temperature anemometer schematics, or CTA, where the TFPT replaces the hot wire. The TFPT 0402 ohm is placed in a Wheatstone bridge. Another TFPT, ohmic, is used in the other branch of the bridge in order to bring a correction for ambient temperature changes. At time 0, R1 is used for balancing the bridge. When there is airflow change, the bridge voltage is unbalanced and the output voltage of the PI circuit is used to rebalance it. We are going to see now if the output voltage Vout can be used to detect the airflow despite all circuit tolerances. The answer is positive, as there is a gap of 0.3 volt between the levels of Vout in still air and with airflow. With all these results, we can visualize separately the influence of the ambient temperature on the result and the influence of the TFPT electrical tolerances. Well, this ends up the part 6 of the video series. I hope that you enjoyed it. Thanks for watching.